Splitting. My splitting headache, my splitting attitude toward the NMR lectures. But I want to talk about why splits happen, right? So we've went through these examples of this main signal being split into multiple smaller ones, some a little bit lower and some a little bit bigger. And I want to go through this conversation about why splitting actually happens in NMR. What causes it to show up in the spectrum when we begin to take a look at the molecular structure and compare that to the actual NMR spectra. So what you're seeing on the screen right now is just a focus really on this CH3 group, and these protons all are equivalent, right? We know that now from all of these other previous lecture videos. And these equivalent hydrogens, there's 3 of them, so that is going to cause a signal. Where that signal happens, I don't really care, and I don't think that you want to care either. But what we're focused on here is the idea of splitting and why is it occurring. So next door, we go to that carbon and we say, hey carbon, how many kids you got? And that carbon's going to say, I've got 1. So 1 plus 1 is 2. So this signal that we get, normally it would be 1 signal and that is it. That signal will be split into 2 separate ones. So the question is why? Well, we start off this basic because I think that it allows us to explain this a little bit better. But these protons have a spin that's associated with them to create that signal. And then when you go next door, that next door carbon had 1 hydrogen, right? So we've talked in the very initial stages of the NMR videos, we talked about this idea of maybe an alpha and a beta spin, or aligning with the field and aligning against the field. So what will happen here is that proton's got a choice. That proton can align with the field or it can align against the field. We get different spins kind of that are happening from this as well. So this main signal that we get from those 3 equivalent hydrogens, depending on what's happening next door, it could amplify that signal that we're seeing. And if it amplifies, then we get a slightly higher signal on the ppm or the delta scale. Or this spin could actually counteract what we're seeing, and that spin could actually be a little bit more upfield, a little bit lower in part per million because of that. So it's counteracting that experience or that ppm from that main signal from the CH3. So that's why splitting begins to happen. And as you can imagine, well, in this example, we just had 1 hydrogen and that is it, right? But what if the next door carbons, what if they have, 3 hydrogens or 4 hydrogens? Well, this is the concept of why things are splitting in more than 2 signals, because each one of those hydrogens could be aligned with or against the main signal. All right, so for example, here's another type of molecule, and this one has 2 chlorines, right? And those 2 chlorines are like, okay, well, that's kind of what we had here, but we're focused on a different proton. So those 2 chlorines are having an effect on that hydrogen, and this hydrogen will give us 1 signal, and here is our signal right there. So next door, we go to a different carbon that has different protons, and we look at those protons, and we say, protons, we know that you've got kids here in the house, you're running around in the front yard and the backyard, but, are you all running in the same direction, yes or no? So here we've got 3 different choices, right? One of those protons could be pointed up and the other 2 could be pointed down. Or one could be pointed up, the second one could be pointed up, and maybe that one could be pointed down. Or maybe all of them are pointed up. I don't know. Or maybe all of them are pointed down. So the idea here is that, quite honestly, like all of these versions, all of these variants are out there and they exist. So here we see different possibilities, different opportunities for these protons to spin. And if they're spinning with the main signal, then it begins to amplify that signal on higher and higher ppms. Not by much, just a little bit. But if they go against that spin or that signal, then they will go lower and lower from that main signal, and they will go lower in ppms on the delta scale. So we see this nice spread. We see kind of the main signal, or somewhat the main signal, toward the middles of these major shifts. And then there's a few lines in front and there's a few lines in back. And now we know why those lines are existing. We knew that they were tied to the protons that were different. However, the reason that they are different locations is because they are amplifying or decreasing the main signal from that particular proton that we're interested in. And it's all based on how they're spinning. So that's what this diagram in your textbook is going to basically show you. You've got an option here where all three of those protons could be with, and all three of those protons could be against. And then you also have some versions or some variations where these possibilities begin to show up. These are 2 with and 1 against. So the first 2 could be with and the last one's against, right? Or the first one is with, the second one is against, and the third one is with. It's still 2 with and 1 against. Or the first one is against and the other 2 are with. It's just possibilities. That's all that they are. They are randomized possibilities of what could show up. So what you're seeing here is that there's more options for these, right? We've got more variations, more possibilities. If all of them are with, there's only one possibility. So we typically see a very short signal in the beginning with that. However, if 2 of them are with, it's going to amplify that main signal. And there's more choices here in order to do that. There's 3 choices versus 1. So that signal will be a little bit higher because of that. So that's why we see the heights the way that we do when we look at splitting of a major signal. Then, here in this case, 2 of them are against. Well, that means if I'm looking at one major signal, if 2 of them are against that signal, it might lower the ppm value. But we still have 3 possibilities in order to get that done. So because of that, we typically see another shift or a split in that shift that will be about the same height as the previous one, right? And then finally, we have an option where all 3 of them are against that main signal. And if all 3 of them are against that main signal, we get another signal that will be even lower, and it will be about the same height as the first one where all 3 of them were with the main signal. Okay, so this is why we start to see the shapes that we actually begin to see, and that is how these are related. Okay, so now you know that the options for all of them to be with and all of them to be against the main field are very low, and these are typically the shortest signals that we see on the extremities. And then the possibilities of the middle ones: 2 against, 1 for, 2 for, 1 against. It doesn't really matter, but those are possibilities that exist. There's more options for those, and because of that, these splittings are happening at a much higher height, right, or intensity value. So that is really why splitting occurs. That's what begins to go on. The problem here, though, is that we have another little tricky thing that goes on here. So with all of the splitting, every time that we've talked about splitting in the past few videos, we talked about neighboring carbons, right? So this carbon has a hydrogen on it, and next door to that is a carbon with another, at least 1 hydrogen on it. So these do split each other's signals. And the reason is because they are separated by that neighbor, that 1 carbon that's next door. And then if you look at this middle one, well, this carbon and this carbon is a little bit further apart from each other. So if I take a look at this hydrogen, well, this particular carbon in the middle, if there are hydrogens on that carbon, that will split the signal from that proton, right? That's what we've always done up until this point. But never did we go another route over. We didn't go another step. We didn't go another neighbor, 2 doors down, like the Dolly Parton song. 2 doors down, we're laughing and drinking and having a party. Okay, so you know that song, right? If not, you need to listen to it. Go YouTube, Dolly Parton, 2 doors down. And think about NMR that we just did here as an example. All right, so this carbon is actually the second one down. And that carbon doesn't really have an option to affect the main signal from the proton that we have labeled as A here. It's too far down. So we never really include those. We only include the adjacent ones. However, there is an example here that is a little tricky, and that's when double bonds are included. So with double bonds, you get this very rigid kind of up and down orientation, cis and trans, E or Z types of grouping that happens on the double bonded carbons. And because of that, this hydrogen, that proton, if we go next door and we look at this carbon, well, we would normally count those carbons and we would say, you know, this carbon's got 1 hydrogen, so there's a possibility for that to be different. So it is a non-equivalent hydrogen, and because of that, we might get a splitting in the signal. However, here, we do sometimes go to the next carbon over. And the reason that we do that is because this proton that might be on that second carbon down, 2 doors down, Dolly Parton carbon, these are really close together based on the orientation that it has. So I will try not to give you examples that go into detail with this. We are now getting into the extremities of the NMR world, but keep in mind that double bonded carbons, based on their orientation about how they're made structure-wise, those 2-door down carbons, the Dolly Parton carbons, those Dolly Parton carbons can have protons on them that are greatly nearby. So that means these two hydrogens are almost like next door to each other, like if it was really next door to each other. And because of that, they can affect how each of them begin to split. So just keep in mind that NMR is not perfect. NMR is not going to be a, yes, this is a definite every single time that we do it. There's all of these exceptions that are out there that begin to happen. And these exceptions we have to kind of start looking at and just taking it with a grain of salt and moving on. So this is not by far the way that we identify chemical structure, but it's just one tool that we can add now to our MS and our R tool to identify or help deduce a structure of a compound that was analyzed. So here we get an NMR, and with the diagram that they give us here up in the top left, we see two major signals. We see a signal here in the middle, and we see those two equivalent signals on the end. And then if we look at the signals on the end, which would be B, they are the closest to the electronegativity ones, right? So that means that this is probably further downfield. It has a higher ppm value associated with it. So if I look at this, this is a signal that we're getting next door to that carbon. We have two hydrogens, and those two hydrogens there, they are 2 + 1, which is going to be a 3, right? And if we zoom in on that signal, we actually see that triplet take place. So that one makes sense for us, right? So that one we feel good about. It makes sense as far as the lecture material goes. It goes hand in hand. There's no really funny things that are happening here. Now, if we look at the middle signal for A, this is the furthest away from the electronegativity atoms or electronegative atoms, and that A is going to be here. So that's the signal there. And then if I look to the left, I see 2, and in the past we did like 2 + 1, and then that's 2 + 1, which is 3. And then over here we say, well, wait a minute, that's an equivalent one, right? So because they are equivalent, they are basically giving me the same signal, and they're not different signals. So how do we handle that? And then if you do another 2 + 1, which is 3, and 3 × 3, which is 9, no, that's wrong. That's not what you do. So what happens here is that we start taking a look at these equivalent hydrogens, and that changes the way that the splitting begins to happen. So we've got 2 protons on the left, we've got 2 protons on the right, right, those are equivalent to each other. So 2 and 2 is going to be a total of 4. And then if you look at the splitting or the way that this happens, that is a 1, 2, 3, 4, and 5. So this is a pentet. And I need my mouth to work this morning. So this is going to be a 2 on the left, a 2 on the right. And because they are equivalent, we only add the 1 once. So 2 plus 2 is 4 plus 1 is going to be a total of 5. So we see that splitting take place. And that splitting is taking place like normal. That's what we would kind of suggest would happen in an actual NMR. So nothing tricky. Everything follows through with whatever that we've talked about so far up until this point. So let's keep looking at some of these examples. Here I see 1, 2, 3, 4, maybe 5 major signals, right? So here I see a signal, there's another, and then this really big tall one that happens there, and then the one right beside of it. So it looks like I've got 5 signals. I hope that I get 5 different protons or proton types in the structure. And if I look at the way that they've labeled them, I see an A and a B and a C and a D and an E. So there are 5. And again, just like all of the other previous examples, they go in order with these. Okay, so let's take a look at the A. And the A signal is from that CH3 group. So that CH3 group has 2 kids that live next door. So 2 plus 1 is going, maybe I should have always said 2 plus 1, where 1 is the mean mommy or the mean daddy that try to get those kids rounded up in the house all the time. So those 2 protons plus that mean parent. So that will be a total of 3. So if you look at that particular signal, you can kind of see 3. They did not really blow that up for you. They just kind of left it little bitty tiny things, and you got to squint your eyes to see if it's actually in a triplet. But you can at least see 3 major kind of pieces there. Then let's take a look at B. B, we've got some equivalent protons. There's a lot of them, right? There's 6 of these protons, and that's why that line is much taller. And then beside of that one is this 1 hydrogen, that neighbor that has 1 kid with 1 mean mad parent. So that's going to be a total of 2. That's going to be a doublet. So here is the signal for that I've labeled as B. That's happening at about 1.3, 1.4. And then here they've enlarged that for you. And you can tell that by looking at the unit down here at the bottom. It goes 1.1 to 1.3. So this is a double, and that makes sense. That's what we would predict. So far, there's no really major surprises that are happening here. Now I want to take a look at this signal that's happening between 4.8 to 5. So 4.8 to 5 is going to be this signal here for E, and that's that one. All right, so they've enlarged it for you so you can see the splitting a little bit better. And then if I look at E, it's talking about this particular proton right there. Okay, so if I look at this particular proton, I look at the adjacent neighbors that are nearby, and these are equivalent hydrogens to each other. So I've got 3 hydrogens on one side and 3 on the other, but they are equivalent. So I'm only going to add one time. So this is 3 plus 3, which is 6 plus 1 is 7. And if I take a look at the way that this is splitting, I see 1 and then 2 and then 3 and then 4, and then 5, and then 6, and then that little one down there, which is 7. So this is a multiplet, and that multiplet is going, because they're equivalent protons, 3 plus 3 is 6, plus 1 is 7. All right. So again, no surprises, nothing really happening here at all. It seems like a general review of everything that we've talked about, and it should be. And there's only very few exceptions that are happening out there that we would actually introduce for you. Okay, so here's another example problem, and this one does involve a double bond. So if I take a look at the major shifts, I'm looking at maybe 1 and then 2, possibly 3 there, and then 4. So maybe 4 different equivalent hydrogens that we are seeing, or proton types that we're seeing. And if I look at the structure, sure enough, I see A, B, C, and D. I see 4. So here is A, and of course A would always be the first one. And then B, there's B, and then C is on the same side just down below, and then D is there. All right, so a couple of tricky things are happening here. First off, we've got this bromine on a carbon, and it looks like that one is going to be the furthest away from electronegativity, right? And why aren't these other two hydrogens over here to the left furthest away from electronegativity? Why wouldn't those be A's? And the reason is because they are directly connected to a carbon that has a double bond. I mean, that truly is a negative source right there. We're not talking about electron greedy. We're talking about electrons that are there. So that double bond position that has those hydrogens on it, those hydrogens are affected quite dramatically versus the hydrogens that might be on a carbon, which is then onto a bromine. And then D is the closest one not only to the double bond, but also to that bromine that is as well electronegative. So that's why we're starting to see a little bit of pull on D, which makes it even more exposed versus that CH2 group that's just directly connected to the bromine and then to the carbon double bond. So this is kind of the concept of what goes on. These NMRs are not going to be very clean cut every time, and I want you to realize that they are not perfect. And then in addition to that, Lord have mercy, look at this at number 6. I mean, this is going to be probably for D, and I take a look at the neighboring carbons. So those neighboring carbons here, these are not equivalent. They're actually different. So it's almost like I would do a 1 plus a 1, and then here would almost be like another 1 plus a 1 because they are not chemically equivalent or the same, so I have to treat them separate. And then over here is a 2 plus 1, and that will be 2 more protons. Those are equivalent to each other, so that's a 2 plus 1. So that's a 3, and that's a 2, and that's a 2. And we said that we just multiply all of these together for multiplicity. And that's why we called that. So 2 times 2 times 3. So 2 times 2 is 4. 4 times 3 is 12. If I do 3 times 2, which is 6 times 2, that's still 12. Doesn't really matter the order that I multiply them in, honestly. It's still going to be a multiplet, and that multiplet here is going to be 12 signals. And then if I look at this, and I look at that signal and it says, what is the splitting? I mean, if I look at that thing, it's just like a, I mean, that's what it looks like to me, right? So there's a bunch of lines, a bunch of splitting that's happening, and there should be a lot because there should be 12 different splits that's happening in that major signal for that carbon bonded to the hydrogen in the double bond. All right. So once more, here we see maybe a few tricky things that go on. I try to stay away from those, though, especially in an Orgo 2 class. These are things that are meant for really advanced organic when we start getting into the nitpicky details of what's going on here, and I try to stray away from those. So in these problems, if you are doing a problem and it's not quite 100% matching, I want you to understand that it might not be a 100% match, and the reason is because of all of these little bitty tricky things that can go on in the NMR world because of that. So in the next video, we'll continue the idea of splitting. However, I want you to take a stab at these example problems first. So here we have 4 example problems, A, B, C, and D. And then with these example problems, the problem's going to say, state the number of signals that you're going to get, and then state the multiplicity of each of these signals once you determine how many that you have. So again, they're looking for a doublet or a triplet or a quartet or a pentet and so forth. So how many ways will it split with each particular signal that you have identified? So take a stab at these, see if you can do these on your own, and then in the next video, we'll pick up with A, B, C, D, and we'll do those answers for you so that way you can compare what you did to what the true answers are and see where you messed up if you did. But I don't think that you will. I think that you'll get these 100% correct, unlike interpretation of NMR.